Hey everyone, welcome to my section. I'm going to be trying to teach this way, where I would record a lecture and then you can watch it whenever you like to. The reason I wanted to do that was because when I was taking classes, I didn't always like having so many appointments during the week. There's a lot of work to do, and a section, should kind of be a place where you get your questions answered. But the way that this class is structured, at least with the sections, usually you'll go to section, you kind of get some answers to homework or something like that. But Yvonne doesn't assign homework, so that makes it a little bit difficult for studying. Assigning homework is kind of like a double-edged sword, or maybe I should say it's a mixed blessing, I guess, that you don't have homework, because then you don't have to do anything. You get more time to do other assignments or whatever you would like. But the downside is that it's not really like you'll learn much that way. So I am going to have some suggested problems that you work through. I'll try to work on some of them with you, I will give probably the answers to all of them at some point, but it's probably good if you would try to do them so that you can get some practice with calculations, because you are going to have a test, I'm pretty sure. And then if you have to do the test, you've never done the calculations before, it might be surprising, some of the tricks, because this class is different than other classes that you've had. So let me get started kind of with what slides I have. The previous classes you've had come from the frequentist perspective of statistics. This class is probably going to be a Bayesian class because Yvonne's Bayesian, so it's going to be a little bit different than other classes that you've had. Bayesians approach statistics in a different way. And why is there a difference there? Frequentists and Bayesians, the difference, I would put it, is in their view of probability. Frequentists view probability as a fixed quantity. You don't try to estimate that quantity. Well, you do try to estimate it, but you don't try to put a distribution on it like Bayesians do. What you do is you'll gather data and you'll try to estimate one number. Bayesians don't do that. Bayesians will try to estimate a distribution, and then the point estimates that come from Bayesians are sample moments of that distribution. So that's how they can both get point estimates. You can get like a mean from the frequentist perspective after observing data, and you can also get a mean from the Bayesian perspective. But it's a totally different approach. For example, if you think about tossing a coin, well, the frequentist would assume that there is one number that is the probability of a head or a tail. A Bayesian wouldn't. A Bayesian would assume that there is a distribution of numbers that could be the true value for the probability, or the range of values it could be for the probability of getting a head or tails. And those two approaches lead to vastly different outcomes. So frequentists have the view that experiments can be repeated and done over and over again. Bayesians have the view that probability is subjective. So there is like an element of probability is in the eye of the beholder. Bruno De Finetti was one of the people who was critical to the understanding of the Bayesian reasoning, and he said that probabilities do not exist. And what he meant by that is probabilities are subjective. So there is an element of subjectivity in determining probabilities. De Finetti's theorem also makes the Bayesian understanding of probabilities something called coherent. So you can't just make up any old probability that you want. You have to avoid the Dutch book. And a Dutch book is a gambling setup where one side is basically arbitraging the other side. So you can't do that. You have to set fair odds so that there isn't an unfair probability to one party. So the coherent principle that Dave Finetti came up with, coherency, makes the subjective understanding of probability logically reasonable, and the frequentist perspective is also logically reasonable. It just depends on what you believe. Do you believe that all things that you observe and that you might want to use statistics for can be treated in a kind of frequentist setup, like repeating the experiment? For instance, the probability that there'll be rain tomorrow, can you repeat that experiment 1,000 times and get a sampling distribution and then estimate it the usual way the frequentists do? I don't think that you can. So that's one place that frequentists come up short, and there's lots of others, because like in economics, you can't repeat experiments. You can't repeat 2007 to 2008 or coronavirus. These things come up as like freak occurrences, and there is some subjectivity involved in analyzing them. So let's go to like a first example of how Bayesian would do things by writing down the way that they specify their model, the likelihood, and everything. So likelihood function you've probably seen before. Frequentists use those. There's good estimators that come from maximizing the log likelihood function, and Bayesians also use the likelihood function as well. So the likelihood is a function is the joint distribution of the sample. So if you have n observations, you assume that those n observations are originating from some model that depends on a parameter or a set of parameters, theta. However, this is where the two views will depart from one another. Bayesians will set a prior likelihood for those parameters. So like I was saying with the subjective view of probability, frequentists are after estimating just some theta. Okay, they assume that theta is actually just some number. Bayesians, though, put this function here, pi for prior, to represent that there's a distribution of values that pi could be. And my prior knowledge, I don't know much about it maybe, or I know a lot about it. Knowing a lot or knowing a little will specify how tight my prior is, for how tight the distribution is. So if you know it's 1/2, then you can set a tight prior on 1/2. If you would rather more let the likelihood inform your decision, then you can set a sparse prior, a vague prior. Maybe you can put the variance really high, and you can say that I think it's 1/2, and I have a large variance. Don't really know where it is, but it's probably about 1/2. Then you can let the likelihood and your sample do most of the talking. The next part that you'll be seeing a lot of from the Bayesian paradigm is the posterior. And posterior is a distribution of the unknown parameter again, but this time conditional on y. And so this is what you're going to be getting after you do like a Markov chain Monte Carlo method, like give sampling or Metropolis Hastings, which we're going to do later. You can even derive these sometimes analytically, just by using calculus, like integrating things. And we'll start there. We're going to do some analytical posteriors. There's also the marginal likelihood. So these 4 things constitute the bread and butter of Bayesian reasoning. You have the likelihood, prior, posterior, and the marginal likelihood. And this is like it. The marginal likelihood is the integrated likelihood and prior. Okay, there should be a D here, but you know what that means. You're integrating out the unknown parameters, and you're getting a number that depends only on the observed data. This also should be an X. So mx. So you don't want anything unknown anymore. This is just a number. And another thing that people will call it is like the normalizing constant. because it normalizes the joint likelihood and prior to be an actual distribution. Okay, the posterior is a distribution that's supposed to integrate to 1, and the marginal likelihood is the number that will cause it to integrate to 1. Okay, so here's an example. This is a pretty simple example. Consider the number of times heads appears in n tosses of a coin. Okay, that's distributed as a binomial distribution. You're going to do n tosses as a probability of p. What is a good prior for p? Okay, so think about what values p could take, and that would help you specify your prior. So here's a common solution to this. It's a probability, so it needs to be between 0 and 1. A good distribution for this would be the beta distribution. And if you know anything about the beta distribution, its support is between 0 and 1. And you need some parameters to specify the beta distribution. Okay, you need an alpha and a beta parameter. And we can let p be distributed as a beta distribution. So now what you'll do to derive the posterior distribution is something that you've probably learned in class already, is you'll multiply the likelihood times the prior, because that'll give you the joint distribution of the likelihood and parameters. Okay, and this is coming from Bayes' theorem, which I'm sure that by now you've probably done it or seen it before. And it'd be good practice if you derive this posterior distribution on your own. So what you're looking to do is to derive the posterior, the pi of p given x, here x. And that would be good practice for you. You can see that it's going to be pretty easy because you have p here and here. You can combine those. You can combine 1 minus p here and here. And then you have some other things that don't involve p. And I'll show you a trick, a Bayesian trick here. Okay, if you want to derive the posterior distribution, you'll see this symbol a lot. You're going to see it a lot if you read about Bayesian stuff, and you'll probably see it a lot in this class. Okay, this is going to be your friend. This is the proportional to sign. In LaTeX, it's \prop2 if you want to write it out. This sign means that it's proportional to a constant of proportionality. So you can basically just drop everything out that doesn't have p in it. And you don't need to do it. You don't need to even worry about it. Anything depending on p can be dropped out, okay? And the reason why is because all of the other things in this expression merely make the distribution integrate to 1 to make it a proper distribution. But you don't care if it integrates to 1. And the reason why you don't care is because consider like a normal distribution in your mind. The normal distribution is a nice distribution. It integrates to 1, of course, because it is a probability distribution. And the reason it integrates to 1 is because you multiply it by the square root of 2 pi divided by the square root of 2 pi sigma squared inverse. Okay, if you did not have that 2 pi sigma squared in front of the normal distribution, then you would not integrate to 1. You would integrate to 2 pi sigma squared, square root. That would be what the integral would be. But you want it to integrate to 1, so you divide by that. That causes the distribution to integrate to 1. But the mean, if you think about the expectation of the normal distribution, the mean is still the same, whether it integrates to 1 or whether it doesn't. It's just more peaked if you don't integrate to 1. So you get the same point estimates and confidence intervals and everything, even if it doesn't integrate to 1. So that's why you can ignore them, and you can worry about the constants of proportionality later, or not at all. So that's why we use this symbol when we're going to be taking this class, when you're doing this class. You see this a lot. And the posterior distribution turns out to be another beta distribution with these updated parameters alpha hat, beta hat. So now you're updating your prior with the sample, and you get these new updated hyperparameters. Okay, the parameters of the prior distribution are called hyperparameters. And now now that we have this distribution, we can also get the marginal likelihood, or the marginal distribution of the data. We can integrate out the parameter p. Like I said, you will want to integrate out this to get the marginal likelihood. And these are the steps that you do. Integrating out p. Okay, this is looks like a beta distribution, except some notation is missing here because it should be, I think, alpha minus 1 and a beta hat minus 1 for it to be a beta distribution, but I'll check that later. But the basic steps are you have another beta distribution, so you can integrate it, and this is the result that you get. Now that you've done those things, you have everything that you need. You have those 4 quantities that are important, but you're probably just going to really be focusing on the posterior or the marginal likelihood after you've done that. You can use the posterior distribution to say something about the density, about P's density. For instance, you can take an expectation and get an estimate of the probability of a head or a tails, and it will be the mean of a beta distribution, which is this, and with the marginal likelihood. Okay, you can compare models, which we'll learn about later, do some model comparison, and you can update on new values. So if you get another set of x's, you can update your previous understanding of p with the new sample. What's cool about this is that you take the posterior from the last step, and that becomes your prior, multiplied times the likelihood, the new likelihood. You get another beta distribution, right? And that will be the update. Okay. And you can also make predictions. So how do you do that? There's something called the predictive distribution too. So we know we want x to show up heads. So given what we already know about this, the predictive distribution becomes this quantity here. Okay, so x hat is the out of sample prediction that we want to know what we want to make a prediction for. And we have our posterior distribution, where we'll have an estimate for the distribution. And this is what we're after. Oh, if I click, I go forward. The predictive distribution of the out of sample x based on the in sample x. That's what we're after, and that's what the predictive distribution is. And that's what point 3 here says. The predictive distribution is the conditional distribution of the prediction given the sample. Okay, so let's do that integral. This is how you'll do that integral. So you'll have this one more toss. You want to know what is the next chance of getting ahead. Well, that's a Bernoulli distribution. It's not binomial because there's only one toss. I said, what's the probability of the next toss that you see being heads? So I'll give it like a different function here. So what's the probability that x hat equals 1? Well, we know that's p, okay? And p is the value that we got from the posterior distribution. Okay, so do that integral. You have the beta function. This is a symbol for the beta function. You can look that up on Wikipedia, what that is. But it's basically gamma alpha hat, gamma beta hat divided by gamma alpha hat plus beta hat. And you have the inverse of that, so you can flip it around. So take the integral with respect to p, and I've multiplied by another p, because that's this p here. That's the probability of another head. Integrate that out, and you get this beta distribution with alpha hat plus 1 this time. And this is the result if you divide those two and cancel out all the gamma functions. You'll get something alpha plus x, alpha plus beta plus n. So you kind of get a ratio of x over n, which is what you would expect it to be. And you have a ratio of your priors. Okay, so you have like priors and what you've actually observed. That's how a lot of Bayesian, I think that's pretty much how every Bayesian predictive distribution will be. Every Bayesian update will be. It'll be some weight of your prior and some weight of the data. So this is basically the basis of the Bayesian process. You'll define your model. That model will determine your likelihood function. You will pick priors, and those priors will you'll usually pick them to be conjugate priors. There's a whole wide range of priors that you can pick, and they have different schools of thought on that. There are different schools of thought on that. Some people suggest picking one kind of prior, and another school of thought suggests picking a different one. I would suggest probably going with the conjugate priors. And a conjugate prior is a prior where if you use the conjugate prior, you'll get a posterior distribution that is also of the same distribution as the likelihood. And that's nice because if you use other kinds of priors, you'll get some awful distribution or some unknown distribution or some posterior distribution that doesn't even exist. Those types of priors are called improper priors. Like if, for instance, you pick a prior that is like, just let's say we picked a prior for the coin toss example, and I just pick the number 1/2 as a distribution. Everywhere it's 1/2. That could be an improper prior. I don't know what happens because I haven't actually used that prior before, but I assume it's improper prior. So improper priors are improper because once you derive the posterior distribution, the distribution integrates to infinity. That's very problematic. And the reason it's so problematic is because a lot of Bayesian inference relies on MCMC sampling. You can't derive a lot of these things analytically. And if you use improper priors, you can sometimes get conditional distributions that are fine, except that if you have an improper prior that integrates to infinity, the result can be totally wrong. And there's a whole strand of literature about that you can read about. So improper priors are not good. There are also some priors called Jeffreys priors, and there's lots of others. But usually what happens in the majority of contexts is that you'll pick a prior distribution to make the posterior conjugate, to make a conjugate posterior. And that will make things easier. And then you'll figure out the posteriors after you do that. The conditional distributions or the joint posterior. And in the example that we just did, the priors were conjugate and the posteriors were easy to find. So we had like that beta binomial model. That made it nice. This is usually not how it goes. Usually a prior, can't be conjugate, or maybe some of them are conjugate and others are not, you'll have to do other things to find the posterior. Like there's some methods in MCMC sampling where if you don't have a distribution that's easy to deal with, you can use Metropolis Hastings. And if that happens, the marginal likelihood is usually even more difficult to find. And we'll deal with estimating the marginal likelihood under those circumstances later. But computing the marginal likelihood can be seriously difficult. But it's often necessary to compute it because that's the basis that you use to compare models. So it's very nice to have, but often difficult to compute. Okay, this would be like an example of kind of like a class that I'll do. And now I have more slides here, but these are questions. So these questions are for you to do, and in class I think I'm going to just be available on Zoom. If you have, it'll be like an extra office hour. If you'd like to ask me how to do this, if you're having a problem, you can ask me, and I can help you with some of the derivations, or you can ask me other questions about the class, and we can do that. But consider this like your homework. You should probably be doing one of these problems, or maybe just try to do the easiest one of them, or at least, so that the test won't be a surprise. I wouldn't want that to happen, because likely the questions that you'll get will be something like this. This first one probably wouldn't be a question that you would get because it's very simple, but this one would probably be, number 2 would probably be a question that you would get: derive the conditional posteriors of beta and sigma squared when you have a model like this. What I've done is I've written down a model. It's a scalar version of a linear regression model. Okay, I didn't do matrix notation like Yvonne does. Yvonne's going to do everything in matrix notation. Just started you out with a scalar case, and then I'll do some matrix notation after. I don't really know what's easier. I mean, sometimes I feel like matrix notation is actually easier to do than the scalar versions. I'm not sure. Whatever you prefer. But anyway, try it with a scalar case so that you can get an idea of just working with scalars, and move up to matrices. So here's just a basic linear regression model. One of the things you should notice about this is that beta is conditional on sigma squared, and then you have a marginal distribution for sigma squared, or a marginal prior for sigma squared. This is an inverse gamma distribution, and try to derive the conditional posterior beta given sigma and y, and sigma given everything else for these two parameters, beta and sigma squared. Then you try this model. This is the same model, actually, and this time you're going to derive the joint posterior of both of these, and then the marginal posteriors of beta and sigma squared. And what you should end up with is a t distribution for beta and an inverse gamma distribution for sigma squared. Okay? That'll be different from the previous question. And here's another model. I don't have any subscripts on it, but it's still scalar case. And it's kind of like a random effects model, except there's only like one observation. You can just do it with one observation, it's fine. And derive the likelihood function and priors. So for this one, you can derive the posterior of A, consider it the conditional posterior, and also the marginal distribution of Y. It should be a little bit more challenging, I think. And then here's like a true random effects model. And you have here an improper prior. So see what happens when you have improper priors. Okay, thank you. Hopefully hear from some of you on class time. Thank you.